Okay, so hybridization, once again, finish that up. I don't think that's, I mean, I think it's hard if you have to really explain what's going on, but really you just have to identify what it is in terms of the S, P's, and D's. So that should be manageable. Okay, sigma and pi bonds are extremely easy. Um, and so what you have going on is when you have bonds happening, you have the sigma bonds and the pi bonds are sort of designations for the attachments. And so here's what we have to know. It says a sigma bond, and this is the symbol for sigma. It says sigma bond, it says all single bonds are sigma. So if you've got a sigma bond, so if you have a single bond, it is a sigma bond. So if we go up to this example we just did, that's a sigma bond, that's a sigma bond, because those are all singles. Okay. Now, the sigma bond gets the best spot. So the best spot to attach two elements to each other, two atoms to each other, is right down the middle. So right down the middle, that primary attachment is the best one. So right down the middle. So it says, where's a sigma bond? It is along an axis, which is right down the middle. Now, what the heck is a pi bond? Well, a pi bond is going to be any of the multiple bonds. So if you have a double bond or a triple bond, those are going to be what we call pi bonds. So where are the pi bonds? So this is so if you think about this as like a big fat balloon animal here, like if you look down at this next one, these here, different pen, these don't get that primary spot. So they have to go above and below or on the left and the right. So they actually surround the middle. So like if um, if we have this already and I add a double bond, where does the double bond go? It's going to have to go above it and below it, or to the left and to the right. So the multiple bonds, they just surround the um, the single bond. So like if you have balloon animals, you already got a balloon in the middle. You got to put the balloons above and below it, or to the left and the right. So this is a really good diagram for the pi bond because it shows, okay, the end to end, like this spot here is taken. So now we got to go above and below. That would be a double bond, or left and right of it would be a triple bond. Do you need to know location? Not really. You just need to understand how to count them. Okay, so the best way to do this is just to give every single bond a sigma, and then everything else gets a pi. So what's a double bond? So I'll draw a quick double bond here. So one of those has to be a sigma for the single bond, and then the other one has to be a pi. So a double bond, it has one sigma and one pi bond. And so then we can just quickly draw a triple bond. So this triple bond is going to have a sigma, but then it's going to have two pi bonds because the other two have to be pi bonds. So it has the sigma, the one sigma and the two pi bonds. And there's no quadruple bond, so that's pretty much it. Super straightforward. All right, we got a problem here. It says cyanogen is a highly toxic gas used as a fumigant in synthesizing organic compounds. Okay, so don't breathe it, it will kill you. All right, A, predict a plausible geometry for the molecule. So that's a shape. Remember when we see the word geometry, they're asking for shape. Give a hybridization scheme for the central atoms. Be careful on the test. They do this a lot where they specifically ask for, okay, what's the hybridization of this particular atom? And then how many sigma and pi bonds total are in the molecule? All right, so we got to draw it. So it's not going to follow our normal patterns. So if it doesn't do that, you normally have two central atoms and you make everything else symmetrical. So as best you can. Right. I've given you that much. I want you to pause the video now, and I want you to try to come up with, what do you think the shape would be? It's kind of tricky. What's the hybridization scheme for the central atom? So basically, what would be the hybridization of this, or what's the hybridization of that? Okay, either one. They're the same. So see if you can figure that out, and then count your total sigma and pi bonds, right? Okay, hopefully you paused the video, you tried this. Remember, if you are not trying things, you are just watching me do chemistry, which is not going to help you. So let's go ahead and go through this. So I would dot these up. Make sure everybody has something top, left, right, and bottom of the atom. So top, bottom, left, right. Everything's got an attachment. Get you a target number. So carbons are 4. So 2 of those would be 8. Nitrogens are 5. So our target number is 18. Okay, so we're going to have to do some work here because this is way more than 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oh my goodness. We're going to have to add a lot of bonds. Okay, so when we're adding bonds to this, you kind of have to probably do like trial and error, but if you add multiple bonds here, you just end up running out of electrons. So the only way it works is to add the multiple bonds on the outside. So if I add one here, go with the red. If I had a double here, I can get rid of these. If I had a double here, I can get rid of these. Make that a triple, get rid of those two. Make that a triple. That's all the bonds I can add because I ran out of electrons on the carbons. But if you count this, this is the way to do this. Kind of a tricky one, right? But we've done a lot of dot structures. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's like super tricky, right? So if you couldn't get that, that's okay. But I do think it's manageable. I think it's something you could get if you have a decent handle on this. So let's go ahead and rewrite it. All right, so if you didn't get it, pause it again. Try and do B and C, A, B, and C now. If you did get it, we'll just kind of keep going. Okay, plausible geometry. All right, you probably couldn't get this, but if it doesn't fit any of our shapes, right? Like this is not an AX anything. It's a total disaster. Always go with linear. Didn't follow any of our shapes. I'm going to go with linear. Okay, so that's A. All right, B. Propose a hybridization scheme for the central atoms. So we are either looking at this one or this one. You pick. I'm just going to pick the one on the left. Hybridization scheme means I need to look at how many attachments it has. So remember, it has one here and one here. That's not 3 attachments. That's 1. You're looking at how many sides of your atom have something attached. So it has 2 attachments, right? So the hybridization scheme, if we do 2, we'd go S, P1, P2, P3, D1, D2. So if I'm only going over 2 spots, the hybridization scheme would be SP. All right. And let's finish up with sigma and pi's. So we have a sigma there, a sigma there, and a sigma there. Because there's 1, 2, 3 single bonds. So every bond has at least a single bond inside of it, right? Now the pi bonds are whatever's left over. So then there is a pi bond for the double and the triple, and then a pi bond for the double and the triple. So you have 3 sigma bonds. 1, 2, 3, and then 4 pi bonds. So to kind of like sum it up, like sigma and pi bonds is just really counting single bonds or sigma, and everything else is pi. Just kind of count them up. So, all right. So let's kind of see where we're at with time. Talk real quick about this term delocalized electrons, and then we're going to go on the next video. We're going to go into intermolecular forces, which is kind of complicated. Really, some memorization pieces you'll have to do, but we'll go into that on the next one. So, what the heck's a delocalized electron? We've talked about it before. Electrons in a molecule that do not belong to a single atom. Delocalized electrons, they get to move. So once again, you're going to find later on that delocalized electrons are the reason that we get shapes. They're the reason that we can have hybridization. They're the reason that we have the ability to do a pi bond where it's kind of going above and below. So anyway, just that term again, sneaky